Okay, Organic Chemistry 2. This is Chapter 12, which deals with alcohols and phenols. For many of you in Organic Chemistry 2, this will be your first chapter of brand new material. We're going to learn a lot of new reactions in this chapter. And so let's get started. Well, alcohols possess a hydroxyl group. Way back in Organic Chemistry 1, we spent some time learning functional groups. And so you would have learned that an alcohol is a compound where we have an R group and then we have a hydroxyl attached to it. So we call that a hydroxyl group. Sometimes I just call it an alcohol group, but a hydroxyl group is the proper term. Examples of alcohols are things like ethanol, which is found in alcoholic beverages. You can have the cycloalcohol, like cyclopentanol that I have shown here. And hydroxyl groups are very common in organic compounds. You can see some interesting compounds here. In this one, we got a cyclobutane, which is kind of cool too. This alcohol is found in the sex pheromone of the male boll weevil. I don't know who took the time to isolate it, but I salute them. The next one is an antibiotic, which has 2 hydroxyl groups in it. Other hydroxyl groups in natural compounds. If you studied biology and you've looked at the phospholipid bilayer and you've seen how there's molecules embedded in that phospholipid bilayer, like cholesterol, which possesses a hydroxyl group. We also saw cholesterol in Organic Chemistry 1 when we talked about stereochemistry, and we talked about the number of stereocenters and the number of possible stereoisomers as a result of all those. What about vitamin D? Ever since the pandemic, vitamin D seems to come up in people's Twitter feeds and on the news once in a while. You need to go outside and get some vitamin D. So here's the structure of vitamin D, which is an alcohol. Geraniol, if you like the smell of geraniums, that's an alcohol. Another one that's in our book, right, a real classic, is THC, tetrahydrocannabinol, which has a phenol in it. So a phenol is when you have a hydroxyl group attached directly to an aromatic ring or a benzene ring. So here's the molecule phenol. You need to know the structure of phenol. It's found in all kinds of cool molecules like dopamine, which is a neurotransmitter that's deficient in people who have Parkinson's disease. What else? Capsaicin has a phenol in it as well. Capsaicin is responsible for the spicy flavor in chili peppers. And of course, THC, and being in Colorado, I'm sure you know where that's found. It's the psychoactive found in marijuana. Well, how do we name alcohols, right? One thing that you find that's a recurring theme in organic chemistry is whenever you discuss a functional group, whether it's alkenes or alkynes, you have to learn the nomenclature associated with it. And so if you understood the nomenclature of things like alkanes, alkenes, and alkynes, you will be able to figure out alcohol nomenclature pretty quickly. The first rule is that we're going to identify the longest chain, but it has to contain the hydroxyl group, just like we saw with alkenes and alkynes, right? It wasn't just a matter of isolating or determining where the longest carbon chain was, like in alkane nomenclature. We have to find the longest chain that includes the hydroxyl group. Then we identify and name the substituents. So that means you have to know methyl, ethyl, propyl, isopropyl, butyl, tert-butyl, sec-butyl, isobutyl. Right? You have to know those kinds of groups, fluoro, chloro, bromo, etc. You assign a locant, which is nothing more than a number and a prefix to each substituent. So is it, a 1-methyl, a 2-methyl, a 3,3-dimethyl, etc. You give the carbon that has the hydroxyl on it, you give that the lowest number possible. So again, you number that longest carbon chain with the hydroxyl given the lowest possible number, and then you list the substituents in alphabetical order. You ignore all prefixes except which ones? There's not just iso, cyclo, and neo. You ignore those as well. When you're ordering alphabetically, so there we go. And then you can place the name of the number for the hydroxyl, its locant, just before the parent name or just before the all suffix. I do it usually just before the parent name. Okay, 99 times out of 100, that's the way that I do it. There were addendums to the IUPAC nomenclature rules, which state you can do it either way, and so either way works with me. So here's some examples. Let's say you have a 5-carbon alkane that's a straight chain. What would you call that? Pentane, right? Well, if you put a hydroxyl on the first carbon, that would not only be a pentanol, that would be one pentanol, right? You'd number the carbons 1, 2, 3, 4, and 5. The reason you have to give it a locant and call it one pentanol is because what if you had this 1, 2, 3, 4, 5, and you had the hydroxyl here, right? That would be 2 pentanol. Okay? Besides calling it one pentanol, you could also call it pentan 1-ol, and that's showing that rule where you can put the locant right before the suffix -ol. Again, I don't do that very often. Okay, now let's say you had this alkane here. You can see that the longest carbon chain possesses 8 carbons, and so the parent would be octane. But if we look at this molecule here, yeah, there is an 8-carbon chain. Sure, that's really beautiful right here. However, it's not the longest carbon chain that includes the hydroxyl. That longest carbon chain has to include the carbon that has the hydroxyl group attached to it. So it only has 7 carbons. So what would this be? This would be 2-propyl, 1-hexanol, right? Because you have the hydroxyl attached to carbon number 1, 1, 2, 3, 4, 5, 6, and then you have a propyl group over here. What else? It says to assign a locant to each substituent. Give the hydroxyl the lowest number, even if you have pi bonds. So you have a pi bond in this molecule here, you just ignore that, okay? You always go by the carbon that has the hydroxyl attached to it, and that is what gets the lowest possible number. So you can see that the numbering on the left is correct, whereas the numbering on the right is incorrect. Again, the locant for the hydroxyl is placed either just before the parent name, like this, or it can be placed just before the "ol" suffix. Again, I do it this way most of the time. Most of the time, you'll see me do it that way. What if you have a cyclic alcohol? Right? If you have cyclopentanol, well, that carbon that the hydroxyl group is attached to, that is assumed to be carbon number 1. So let's say you have a substituent, or substituent somewhere on the ring. You don't have to say that this is 1 cyclopentanol. It's just cyclopentanol. So you number it in such a way that you give these substituents the lowest possible number. If you had gone counterclockwise, it would have been 1, 2, 3, 4. And so you see that the numbers that I have in blue are actually incorrect. The numbers that are in red that are on the slide are actually the correct way of doing it. So this is a 3,3-dimethyl cyclopentanol. And then we also have to determine the stereochemistry. You can see that there's a hydrogen coming out towards us like this. This would be our highest priority group. This would be our lowest priority group. This would be our second highest priority group, and number 3. So if we're going like this, 1, 2, 3, that's counterclockwise, which would be S. But since the hydrogen is coming out, it's reversed, and so it has the R stereochemical designation. So that is correct, R3,3-dimethyl cyclopentanol. We also have common names for alcohols that show up all the time in organic chemistry, right? If you go down to the pharmacy counter at Costco, you can see they have giant containers of 2-propanol, which is rubbing alcohol. The common name is isopropyl alcohol. What about this alcohol, 2-methyl 2-propanol? Its common name is tert-butanol or tert-butyl alcohol. Sometimes I just call it T-butanol. Chemists love shorthands. And then phenylmethanol, well, the common name for that would be benzyl alcohol. So common names are called that for a reason. So common, that's all these names here. It's because they're used most of the time, okay? If you were to go into a lab and say to somebody, a chemist, and say, hand me the phenylmethanol, they would know what you're talking about, but they'd look at you kind of strange. Like, that's a little weird. What about benzyl alcohol? Why don't you call it that? Okay, it's just very common. So I would recommend knowing these 3 compounds and their names: benzyl alcohol, tert-butanol or tert-butyl alcohol, and isopropyl alcohol, which is also rubbing alcohol, as I told you, rubbing alcohol. And there's a cool blurb in our textbook about the antibacterial activities of alcohol. So I encourage you to take a quick peek at that. All right, like halides, alcohols are classified with respect to the type of carbon that they're attached to. So if your alpha carbon is attached to 1 carbon-based group, it's a primary alcohol. If it's attached to 2, it's a secondary alcohol. And if it's attached to 3, it's a tertiary alcohol. So let's say, for example, we had alcohol, right? Just ethanol. Could anybody tell me, would ethanol be considered a primary, secondary, or tertiary alcohol? And it's not a trick. Ethanol. How would you classify ethanol? Yeah, exactly. Ethanol is a primary alcohol, right? Because this is my alpha carbon. Maybe I'll be color coordinated here, right? And this is the 1R group that it's attached to, right? Whereas if I had something like rubbing alcohol, right? Rubbing alcohol is a secondary alcohol because the alpha carbon has 1,2R groups attached to it. If I had something like this, let's say I had 1-methyl cyclohexanol, so this compound here, that would be a tertiary alcohol. Why? Because your alpha carbon is attached to 1, 2, 3 R groups. Okay, so examples of primary, secondary, and tertiary alcohols. Here we go. So you have to be able to classify an alcohol. When the hydroxyl group is attached to a benzene ring, the parent name is phenol. Again, you have to know the name of phenol. It's going to come up all the time in organic chemistry too. So if you had a compound like this where you have the phenol in the molecule, that's your parent, right? And you assume that the carbon that possesses the hydroxyl is carbon number 1. So we have carbon number 1. We number it in such a way to give the other two groups the lowest possible number. So we have a nitro at carbon 2. We have a chloro at carbon number 4. And so this is 4-chloro, 2-nitrophenol, right? We list the chloro and the nitro in alphabetical order. And so you've got to be able to name phenols as well. With that in mind, let's take a look at 12.1C first. Okay, this is a phenol. Could anybody name this phenol? And I'll take the time to circle the phenol in here. And it's not a trick question. Could anybody name that phenol? Pick it out of a police lineup and give it a name. So somebody says 2,6-diethyl phenol. I like the way you think, right? If this is our carbon number 1, we have 1, 2, 3, 4, 5, 6. So we have a 2,6-diethyl, yes, 2,6-diethyl, and the parent is phenol. So 2,6-diethyl phenol. Okay, let's try the next one. It's a little more complex. Let's try B. It's got some stereocenters in here, so let's get to it. The longest carbon chain has 1, 2, 3, 4, 5 carbons in it. So this is some kind of 1-pentanol. So we could scratch that down. It's a 1-pentanol. What else do we know? We have 2 chiral centers, don't we? We have methyl groups on carbons 2, 3, and 4. So this is a 2, 3, 4 trimethyl. So we could scratch that down too. This is 2, 3, 4 trimethyl. But we need to figure out what the stereochemistry is at carbons 2 and at carbon 3. Let's start with carbon 2 first. We start with carbon 2. I'm going to erase the numbers that are on there already. Oops, there we go. Okay, so I'll erase all that. So carbon number 2. Our highest priority group is going to be this carbon. We have our hydrogen going in the back. This will be our second highest priority group. This will be the lowest, and this will be the third. So we go from 1 to 2 to 3, which is going counterclockwise, and so it must be a 2s. Now we need to figure out the stereochemistry for carbon number 3. So that's this carbon right here. If you look at that carbon, you've got a hydrogen going in the back, so that's going to be the lowest priority group. Oops. Lowest priority group there. We've got a carbon that's attached to hydrogen, hydrogen, hydrogen here. You've got a carbon that's attached to carbon, carbon, hydrogen here. And here you've got one that's attached to carbon, carbon, hydrogen. Well, obviously this is going to be the third highest priority, but we need a tiebreaker for the other two, right? So we keep going. And these two are identical. You have a hydrogen, hydrogen, hydrogen. In here you have an oxygen, hydrogen, hydrogen. So oxygen, hydrogen, hydrogen. So this would be the tiebreaker. So that means that this is your second highest priority group. Sorry, your first highest priority group. This is your second highest priority group. So we're going from 1 to 2 to 3, like that. We're going clockwise. And so the stereochemistry at carbon number 3 is 3R, like that. Now we've got all that spinach put together. Now we can put it together in a name, and we end up with the whole thing as being 2S, 3R, 2,3,4 trimethyl, 2,3,4 trimethyl, and then we have 1-pentanol, 1-pentanol. There you have it. Let's try one down here at the bottom. We've got some kind of cyclohexanol. Remember that this carbon must be carbon number 1. We go 2, 3, 4. So we've got a 2, 2, 4, 4 tetramethyl. And we have a cyclohexanol. Cyclohexanol. We need to figure out the stereochemistry at the 1 chiral center in the molecule. So we have a hydrogen going in the back, like this. This would be the lowest priority. This is top priority. Remember, this carbon is attached to carbon, 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 and this carbon is attached to carbon, hydrogen, hydrogen. So my tiebreaker would be here, which would render this my second highest group, this my third highest group. So I'm going from 1 to 2 to 3, which is counterclockwise. So this stereo center is S. I put all that together in a beautiful nomenclature sandwich. And what do I end up with? I end up with S, 2, 2, 4, 4, tetra, methyl, cyclohexanol. Any questions about those? Naming some interesting compounds, revisiting your stereochemistry a little bit. So make sure to review your Kahn-Ingold pre-log rules, which are the rules for determining whether a stereocenter is R or S. Give me a thumbs up if you follow me on that one. Is everybody with me on that one? Cha? No? Anyone? All right, cool. Good. Well, let's move on from there and let's take a look at some commercially important alcohols. Methanol is the simplest possible alcohol. Sometimes we call methanol wood alcohol. So wood alcohol, you'll hear it called that, you know, in old nomenclature or old literature maybe, because methanol was isolated from heating up wood in the absence of oxygen, I think, and they ended up making wood alcohol. Now, again, wood alcohol can get you intoxicated. However, it can cause blindness and death, so it's a poison. So I'd be careful around methanol. Methanol on the industrial scale is not made by heating up wood. It's made by treating carbon dioxide with hydrogen gas, and we make a lot of methanol in the United States every year. Again, methanol is a poison, but it's also used, it is used as a solvent a lot in organic chemistry. It's used as a starting material. And of course, it's used as a fuel. And our textbook has a little bit of a blurb about how in the Indianapolis 500 in the mid 1960s, there was a really bad fire that cost the life of 2 drivers. And so they switched over to methanol. The problem with methanol flames is that they are smokeless. However, they are, since they're colorless, they're virtually, they're very difficult to detect. In fact, if anybody here has ever made fondue before, this is when you buy fondue fuel, it's actually methanol. And if you've ever made fondue, you'll notice that the flame is very hard to see under the fondue pot. Let's see, ethanol is produced from the fermentations of grains or fruits. So I'm sure many of you have studied glycolysis and fermentation, probably in some detail, or lactate fermentation. Anyhow, so ethanol is produced from the fermentation of grains or fruits. We make a lot of ethanol in the US every year. It has many uses. It's used as a solvent, in lots of different reactions. it can be denatured to avoid the heavy taxes that are placed on alcohol that is used for human consumption. Yeah, so there you go. Denatured alcohol is alcohol that contains poisons in it, so it can't be used for personal consumption. Isopropanol, which is rubbing alcohol, is made from the acid catalyzed hydration of propylene. So chemists start with propylene, which is this molecule, and they treat it with acid in the presence of water, and they make this compound, right? Isopropanol. Now, in terms of its antiseptic properties, as far as I know, the antiseptic properties of 1-propanol are even better than isopropanol. It's just more difficult to make. And so that's why we use rubbing alcohol so much. It's also used as a gasoline additive, and other uses include a solvent. So all these little alcohols can be used as solvents in different reactions in organic chemistry, depending on, the type of reactions that you're doing. Physical properties of alcohols. Well, it's important that you understand hydrogen bonding, isn't it? Right? That's a big thing that we covered at the very end of chapter 1 in Organic Chemistry 1. Right? You should know that ethane only experiences London forces. It is a completely nonpolar molecule, and you should know what London forces are. Whereas chloroethane does experience London forces, but it also experiences dipole-dipole forces, right? Because there is a polar bond in chloroethane, whereas ethanol does experience London forces and dipole-dipole interactions, but its strongest intermolecular force is hydrogen bonding, which is a result of the very polar oxygen-hydrogen bond. And so you have that dipole, which renders the hydrogen partially positive and the oxygen partially negative. And so you can draw a hydrogen bond between the partially positive hydrogen atom and the lone pair on an electronegative oxygen. So you need to be fully aware of intermolecular forces, London forces, dipole-dipole forces, and hydrogen bonding. I'm not going to reteach those because they're covered in General Chemistry 1, also in General Chemistry 2 to a small extent, and they're also covered in Organic Chemistry 1. Okay, so the reason why the boiling point increases as we go from ethane to chloroethane to ethanol is because of the increase in strength of their intermolecular forces, right? London forces are the weakest, dipole-dipole are intermediate, and hydrogen bonding is the strongest of these three intermolecular forces. Are there other types of intermolecular forces? Yes. There are other ones that you would have covered in General Chemistry 1, like an ion dipole or an ion-induced dipole. We don't cover those in Organic Chemistry 2. They don't come up a whole heck of a lot. And so you don't have to stress about those. Well, I told you that there was the capability of an alcohol participating in hydrogen bonding. However, what if you have a hydrophobic region in your alcohol, right? Like a molecule like cholesterol, it's got a big hydrophobic portion. Well, if you have something like methanol, which has this little hydrophobic region, methanol is completely miscible with water. What does miscible mean? Miscible doesn't mean soluble. It means mixable or soluble, mixable in all proportions. It's always going to be soluble in water. That's what miscible means. So alcohols that have 3 carbons or less, so methanol, ethanol, isopropanol, these will be miscible in water in all proportions. However, what happens when you have a molecule like this? Here we have 1, 2, 3, 4, 5, 6, 7, 8. So this is 1 octanol, right? This is a primary alcohol, but it's got a really long hydrophobic region. Well, 1 octanol does not mix in water. In fact, it's completely immiscible. If you mix 1 octanol in water, you'll see 2 phases formed. And the reason why is because the hydrophobic portion is so large that it basically negates the fact that you have a hydroxyl group that is capable of hydrogen bonding, right? Because of this giant hydrophobic group, it's going to force it out of, or force it to be insoluble in water. And so you see that the longer the hydrophobic portion in your alcohol, the less water soluble it will be. This is what I was referring to when I said there's an interesting blurb in your book about antibacterial activity and the size of a hydrophobic group. I've never really asked students about this, I don't think, but you see that antibacterial activity. Now, we're not talking about water solubility here. We're talking about the potency in terms of being an antibacterial agent. It increases when you go from methanol, ethanol, propanol, butanol, pentanol, hexanol, heptanol, up to octanol, has the maximum antibacterial activities, and then they drop off pretty sharply after that. And there's some interesting reasons why. It's because in order to kill a bacteria, an alcohol has to have the polar region to do that, but it's also going to have a hydrophobic region in order to penetrate a cell membrane, or the cell membrane of the bacteria. Anyhow, kind of interesting here. Hexylresorcinol is used as an antibacterial and an antifungal agent. Why? Because it's got a good combination of, you get a couple of polar groups over here, but you also have this big hydrophobic portion here. And so it's just finding that balance, right? That's a lot of what drug discovery is, finding the balance between solubility and lipophilicity. I don't know if any of you are familiar with The Far Side, authored by Bob Larson, who's a famous cartoonist. But when I was in industry, we used to have a picture on our office door that said, it had a picture of the devil with a pitchfork behind this guy, and we said Joe Chemist on the guy's back. One door said damned if you do, damned if you don't. And one of them we wrote solubility, and on the other one we wrote lipophilicity. So kind of a medicinal chemist's humor there. All right, well, let's move on and talk about the acidity of alcohols and phenols. Way back in Organic Chemistry 1, we spent a whole chapter talking about acids and bases, and we talked about the pKa's of alcohols, and I introduced you to the concept of area, atom, resonance, induction, orbital, and we discussed how we can qualify relative acidity using area. Well, in order to deprotonate an alcohol, you've got to have a strong base to do it. Sodium hydride is often used to produce an alkoxide, right? Hydride is not a polarizable ion, but it is a good base. Okay, so it makes a crappy nucleophile, but it makes a good base, and so it can abstract a proton from a molecule like ethanol to produce an alkoxide. Here we have sodium methoxide, right? This is just a good old NaOET that we saw Avogadro's number of times in chapter 11. And not only that, but you liberate hydrogen gas. And so this reaction is completely irreversible based on Le Chatelier's principle, right? If the hydrogen is going up as bubbles, well, it's definitely not coming back into the reaction flask. And so this is a great way to produce an alkoxide. Are there other ways to make alkoxides? Absolutely there are. What if you take an alcohol like ethanol and you treat it with a metal like sodium? That's another way to make an alkoxide. You could make sodium methoxide that way, and you also liberate hydrogen gas. Now, if you're wondering, why, Mr. Dion, do we have sodium ethoxide, NaOET, but when we have the tert butoxide, why is it a potassium salt? Okay, that has to do with the solubility of the alcohol in a solvent where we have these different metals. And so I wouldn't really worry about it. I'm not going to ask you anything about it. It's just important to know that you can use metals to deprotonate. So sodium, potassium, or lithium can be used to make alkoxides. And we'll look at a practice problem, I think. If we don't look at one in class, I have one selected where it asks a question about, drawing an alkoxide. Well, an alkoxide is nothing more than the conjugate base of an alcohol, isn't it, right? If we start out with an alcohol, let's say, here's our alcohol, and we treat it with, let's say, sodium hydride. Well, hydride here is our base, right? And we end up making the alkoxide, which is the conjugate base, right? Plus we have the sodium cation, and we have the hydrogen gas that's liberated. Well, if you compare the relative stability of the conjugate bases of an alkane, an amine, an alcohol, and a hydrogen halide, you see that the stability of these conjugate bases increases as you go from a carbon-based anion to a nitrogen to an oxygen, all the way over to a halogen, right? So if you look at the relative acidity of an alkane versus an amine versus an alcohol versus a hydrohalide, the pKa drops, right? We go from 45 to 50, and they drop all the way down to even -10 for a hydrohalide. So how would we rationalize the difference in acidity between an alkane, an amine, an alcohol, and a hydrogen halide? We would just compare the relative stability of their conjugate bases. I mean, you could just memorize the pKa's, which I recommend doing, but if you ever get stuck, just remember that the more electronegative element is going to better stabilize the negative charge, right? The least electronegative element is going to least effectively stabilize that negative charge. So the less stable the conjugate base is, the least acidic the conjugate acid would be. All right. Well, if we compare alcohols, it says factors that affect the relative acidity of alcohols and phenols. If you compare the pKa of cyclohexanol and phenol, you can see there's a pretty darn big difference in their pKa. Right? You have a pKa of 18 for cyclohexanol. The pKa of phenol is 10. So it's what, 100 million times more acidic than cyclohexanol. What makes phenol so much more acidic? Right? If you draw the conjugate base of cyclohexanol, and it's not on here, it would be this. It's just this, right? We have the negative charge on an oxygen. But what's the difference is that when you deprotonate phenol, you get a phenoxide, and the phenoxide has a greater stabilization due to resonance. Right? We can draw all these beautiful resonance structures here. And remember, we have ARIO, right? Atom, resonance, induction, orbital. Well, atom doesn't cut the mustard because the conjugate base would both have the negative charge on an oxygen for cyclohexanol or phenol. But resonance does cut the mustard, doesn't it, right? Because the phenol produces a phenoxide, which is resonance stabilized. What are some other factors? Let's say we're comparing ethanol with trichloroethanol. You see that trichloroethanol is much more acidic, 10 to the power of 4 times more, so around 10,000 times more acidic than ethanol. Why is that? If we draw the conjugate base of ethanol, it's this ethoxide. If we draw the conjugate base of this compound, we end up with this ethoxide. Well, the difference in stability of the conjugate bases can't be decided by atom. It can't be decided by resonance because there's no resonance structures. However, it can be decided by induction, can't it? Right? This conjugate base is further stabilized by the inductive electron withdrawing effects of the carbon-chlorine bonds, which serve to stabilize that negative charge. The last one doesn't involve ARIO. It's solvation effects, right? Let's say you compare the relative acidity of ethanol and terbutanol. It's not much, but there's a difference in 100. Ethanol is 100 times more acidic than terbutanol. Why is that, right? If you draw the conjugate base, you have the ethoxide, you have the terbutoxide. You can't solve it with atom, resonance, induction, or orbital. So how do you rationalize it? It's rationalized in terms of the solvation of the alkoxide. Let me show you. If you have ethoxide, the reason it's more stable and the reason why its pK is 16 or lower, the reason it's more acidic is because the conjugate base is more stabilized by solvent molecules because it's less sterically hindered, so more solvent molecules can gather around that negative charge and stabilize it. If you have terbutoxide, because of the steric effects of having the 3 methyl groups, its pKa is higher. It's less acidic. Why? Because you have less solvent molecules that are able to stabilize that negative charge. So this one's kind of interesting. It's something very new for all of my students who took Organic Chemistry 1 with me. Well, with all that in mind, let's try a practice problem and see if we can identify which molecule is more acidic when we're given a pair of molecules and see if we can figure out why. Let's start with 12.5a. We have a primary alcohol and we have a tertiary alcohol. Could anybody tell me which one of these would be more acidic? And tell me why? Does anybody have an answer? I don't think it's the tertiary, right? I don't think it's the tertiary because if we compare the relative stability of their conjugate bases, the primary is going to be more acidic. More acidic. Why? Because when you draw its conjugate base, son of a gun, 1, 2, 3, 4, 2, 3, 7. When you draw its conjugate base, it's going to be stabilized by more solvent molecules, right? More solvent molecules will be able to get around and stabilize that negative charge. Whereas if you have the tertiary, right, because of those big R groups, right, you have less solvent molecules that can gather around. And so it's the primary that's going to be more acidic. Take a look at the next one while I'm fixing up my artistry here. Okay. What about the next one? Could anybody tell me? I'll call the first one A, and I'll call the second one B. Could anybody tell me which one of these would be more acidic? And tell me why. We have this pentachlorophenol. Anyone? Yeah, exactly. And why is it? A, because, we'll say A, due to induction. Right, you have all of these electron withdrawing groups, right? All these chlorines that are going to suck electron density away, which will serve to stabilize the conjugate base. The next one is kind of an interesting one. If we call this A and we call this B, could anybody tell me which one of these would be more acidic? Which one would be more acidic? The answer is B. B is more acidic because it has one more resonance structure. Okay, and you should be able to draw all the resonance structures. Right, if you have this molecule, so we'll draw it out here. All right, and this is just a little bit of a review of drawing resonance structures. Let me fix this guy up here. So if we deprotonate it, we draw the phenoxide like this, and then we start pushing curved arrows around like this. So then you'd end up with something that looks like this. Dang it, I have a real habit of drawing it so that I can't get that acetyl group in there, don't I? So there we go. So there's our first resonance structure. We should be able to push that pair of electrons around. So we make a new pi bond here, put a pair of electrons right here. We end up with something that looks like this. All right, and not only can we move these electrons like this, okay, so we can put them up here so that we have something that looks like this. But we also have one more resonance structure, don't we, where we can put the pair of electrons right here. So we'll draw that resonance structure like this. There we go. And there you have it, like that. So phenol doesn't have this extra resonance structure, does it? You can't draw that extra resonance structure. So it's based off of one extra resonance structure for that one. And the last one, if I call them A and B again, so I'll call this one A. No, let's call them what they are. So this is tert butanol, and this is phenol. Who could tell me which one would be more acidic, tert butanol or phenol? Yeah, absolutely. Terbutanol has a pK of 18. We saw that a few slides ago. And phenol has a pK of 10. So phenol is more acidic due to resonance. Nothing more than that, right? If you look at aereo, it's not atom, it's resonance, all right? If we look at aereo for this one, A-R-I-O, it's not atom, it's not resonance, it's induction. Or shit, it's not atom, it's resonance for this one. And it was this one here. It's not atom, it's not resonance. Okay, it's induction. And for the first one, it's solvent only. Okay, so the first one can't be solved using aereo. There we go. That you can see how that would lend itself to a multiple choice question very easily.